Hey everybody, we are moving on to a new topic within our discussion of electromagnetism. So we're going to be talking about some new stuff today. Last time we talked about the Biot-Savart law, which is how one figures out the magnetic field in different situations. So, for example, at the center of a coil of wire, or if there's some loop of wire that might be a triangle or a square or a pentagon or hexagon, whatever. You can use some of the stuff from that lecture with the Biot-Savart law to figure that out. And there's also questions that you're going to see on the midterm and the final about when you have two very long wires and trying to figure out the magnetic field at some distance from those two wires, which is not actually a Biot-Savart law question. It involves some thought about what direction the magnetic fields are going, things like that. Alright, so that's what we did last time. We also introduced what's called Ampere's law, and you've probably seen an integral right now. Don't be scared by the circle. The circle just means that you're integrating around a loop. So instead of integrating on a line and sort of saying like, x min to x max, it's basically saying, no, none of that. It's going to start from this position, integrate around, come back to where you started is what that circle means. And you're going to be integrating over the magnetic field over ds is some path, so ds is some length. And then this is the current that's punching through that surface. And so we did some examples last time. We're going to do some more examples today because I know this is probably pretty strange and unfamiliar to you at this point, which is fine. And similar to Gauss's law, this is always true, but it's not always useful for helping you to answer questions. So it's useful when, for example, you can integrate something around something. So we had an example of a long wire last time, and if you stay the same distance from that long wire, then by symmetry it would make a lot of sense if the strength of the magnetic field would be the same on that path that you're going, in which case you can take B outside of this as a constant and then integrate it over this, which just becomes a circumference. That's the kind of thing in which this gives you something useful to calculate what the magnetic fields are. That doesn't always happen. There's only a couple situations in which you can do that. But the good news for you is that if you can sort of understand the different situations in which this does give you a simplified expression, well then now you have a blueprint for what in the world is on the midterm, because there's only a certain number of geometries and symmetries that I can do. In other words, a certain number of types of problems, you could say. So last time, as I said, we used Ampere's law to figure out the magnetic field outside of a long wire. I can't remember if we actually used Ampere's law to calculate the magnetic field inside of a long wire, but indeed it can actually help you to do that. And later we might talk about that some more. Alright, we're going to talk about new stuff, such as solenoids, that we're going to continue to connect to our discussion of Ampere's law. So what we really like to know from the situation, we have this wire that's sort of coiled up. We have the current going through the wire, which makes a nice strong magnetic field through the middle of this thing. We'd really like to be able to know what the magnetic field in the middle of this thing should be. The problem is that applying the Biot-Savart law to this case is pretty difficult, because you'd have to break up the wire into tiny little pieces, and at each point the magnetic field is the sum of the contributions of the magnetic fields from all those little tiny chunks of wire. So if you remember how tricky it was, even the simple cases that we did last time, it's even more complicated for this case. So we'd really like something else to be able to help us out. And it turns out you can apply Ampere's law to this case. You might wonder if it's sufficiently complicated that you couldn't, but indeed you can, which is what we're going to do in just a second. But when you apply Ampere's law, you have to make a very good choice for what the Amperian loop should be. which reminds me a little bit of how when we're doing Gauss's law, how Gauss's law is always true. You can define whatever Gaussian surface that you want, but it's usually helpful to. There's some Gaussian surfaces that are more helpful than others, especially if you're trying to figure out what the electric field is using this method. So with Ampere's law, some Amperian loops are more helpful than others. So one Amperian loop that we could draw, which is not so helpful, is this one, which is Ampere, which is outside of this thing. And there's a couple of reasons why it's not so helpful. The main one is that we're out here. We really want to know what the magnetic field is inside of this thing, but instead we're doing this integral all the way out here where the magnetic field is very weak. Again, the distance between the field lines is pretty large out here compared to inside of there. And so the magnetic field's weak, this integral is going to be weak, and not really telling us what we want. So that's one issue. The other issue is the current will be, the current, this is the current through this circle. You could say through this membrane if you want. The current only sort of punches through once there. So if you're going to add up the total current punching through this thing, or the net current, or sometimes I write this I through, ITH, it's current through it. Well, that current's just going to be I. It's not going to be like I times 10 or anything like that. So the current's going to be relatively small through the Amperian loop. The magnetic field is going to be relatively small because it's all the way out here. So this is not such a useful Amperian loop. If our goal is to figure out what the magnetic field is inside of this thing. So what is the right Amperian loop, or a better Amperian loop to figuring that out would be like this. And this is nice because you're actually going through the part of the magnetic field that's nice and strong. And so we're going to integrate over this path. And maybe you remember when you're integrating over x, that if you're going to integrate from x1 to x3, you can break that up into the integral of x1 to x2 plus the integral of x2 to x3, something like that, and that's equivalent. Well, the same idea here is that if you're doing this path integral, you can take each leg of the path and integrate this integral there. And because these are not closed, they don't have the circles there. So what does this tell us? Well, the first part is pretty easy. This doesn't look fun, but the first part is pretty easy, which is to notice that out here the magnetic field is really weak, and so B is going to be pretty small, and that's important because it means that this term here is going to be much less than these other terms, and so we can assume that this is relatively close to 0. The next thing we can do is to talk about the second and fourth, so the second and fourth legs. In a second we'll talk about the third leg. The third leg is important because we're going through the magnetic field, so the magnetic field is nice and big there. So the third leg is really important. We're going to come back to that in a second. But the next slide we're going to talk about 2 and 4. So here we go. So 2 and 4. The thing to note about this is that there's a cross product here. So if you remember back in the vectors discussions, there's a cross product between these two vectors, which means that there's going to be some sort of cosine theta in there, where the theta is the angle between the two vectors. Well, what is the angle between the magnetic field and the path over here? Well, it's 90 degrees. Cosine of 90 degrees, if you look that up, is 0. And so this whole thing ends up being equaling 0. So that means that this term is 0. But there's also this leg number 4 over here. Leg number 4, the path is going this way, but it's still 90 degrees from the magnetic field. And so you are also going to get a cosine of 90 here. Cosine of 90 is 0. This equals 0. So both of these things are going to give you 0. So just kind of by process of elimination, we find that this crazy looking integral is mainly this thing, which is what I'm saying here. The next step is actually evaluate this thing. So to evaluate it, um, we can kind of break it down, and we know the magnetic field is going off this way. We also know that basically because of the symmetry of this thing, the magnetic field should be relatively constant. And any constant that's in an integral, you can bring that outside of the constant, kind of like this, right? And so now we're just integrating over the path. Well, the path is whatever that length is. So you get something like this. And again, we get this cosine theta here. But the nice part is that because the path is in the same direction as the magnetic field, the angle between these two vectors is just 0, and you get a cosine of 1. So there you go. And so, and then this length, I'm going to call this the length of our Amperian loop. I'm going to call that L. And so, from all of this, I'm going to conclude that this crazy-looking integral, just boils down to the magnetic field strength times the length of this Amperian loop. Now, there's one more thing I have to note. There's one asterisk, which is that our Amperian loop does not have to be the full length of the solenoid. It can be shorter than that. So this is just the length of our Amperian loop. It's not necessarily the same length as our solenoid, which I'll talk about in a second. So if I put this all together, in other words, when I connect this to this discussion of the number, how much current is going on here, well, we just showed that this is equal to B times L, which is what's here. And then this N times I, you notice that the current is sort of, punching through at multiple points here. If this is kind of slicing through our solenoid, an imaginary slice, we're not actually breaking the components. So this is what you get. Which you can divide both sides by L and get an expression for what the magnetic field should be, given what the current is. The important thing to mention is that this N is the number of times that the current sort of punches through this membrane. Because this is smaller than the full size of the solenoid, we're sort of like skipping this one, and we're like skipping this one over here. However, the number of times the current punches through this thing and this length, that ratio should be equal to the total number of wraps divided by the total length of this solenoid. So however you want to write it, that's kind of what you end up with. Okay. Now, we use these arguments to calculate what this constant magnetic field is. You might be saying, okay, Chris, it can't possibly be a perfectly constant magnetic field. Well, if you do it in detail, you get something like this, where, again, the distance between field lines tells you how strong the magnetic field is. And yes, indeed, out here the magnetic field is not nearly as strong as it is in here. But the nice part is that it does a decent job of providing a relatively constant magnetic field in terms of the spatial extent of it. So the colors here indicate the strength of the magnetic field, and you see a lot of areas that are sort of this deep orange. So it actually does a pretty good job of maintaining constant magnetic field, in my opinion, spatially. The magnetic field could change with time, because it could be that you're changing this current with time. That's fine. But spatially, in terms of the strength of the field as a position of x and y and z, spatially, as long as you're inside of this thing, the magnetic field doesn't change too much. So often in this context, you'll hear people talk about how it's important to put iron inside of these loops. The reason you want to do that is because iron has this special property in which it is 200,000 times, its magnetic permeability is 200,000 times greater than just the vacuum or air. And so that's interesting because, excuse me, that's interesting because if you solve for the magnetic field, if we did this all over again with iron, we would have to multiply this by 200,000, which means we'd have to multiply our magnetic field result by 200,000, which is really amazing. Now there's limits on how high the magnetic field can get, which is about, I don't know, it's about a Tesla in iron, which is a long story. But if the magnetic field is relatively low, you do get this huge enhancement factor, which is kind of nice. So another thing you'll see, and another example of Ampere's law, is toroids. And so I am not going to actually go through the derivation of how to apply Ampere's law to a toroid. This may be 29.6, I'm not totally sure. I'm not going to go through how to do that, but for sure this is one of the possible applications of Ampere's law for the midterm. So please be on your guard about that. We'll talk a little bit more about these kinds of things next time, but there we go. All right. This may be a segue to chapter 30. I can't quite remember. All right. So let's take a coil. Let's put it into a uniform magnetic field. The magnetic field is not changing with time. So, for example, maybe it's a permanent magnet. So we're not actually changing the magnetic field as a function of time. And we're going to move this coil in different ways, and I want you to tell me whether a current would arise on this wire. In other words, if you had a voltmeter, multimeter on this thing, ammeter, would you get a current or would you not? So the first thing I want to do is just move it through the magnetic fields and see what happens. So do you think there's a current here or no? Tempting? No, there is not a current here. The reason is that, so it's not that the forces on the electrons is zero. There is definitely a force on the electrons. So remember V cross B. So if we're moving this way, if we're moving this way, the magnetic field's into the board. Moving this way, the magnetic field's into the board. That means V cross B would be up, which for electrons QV cross B would be down because Q is negative. So the force on those electrons would be down. The problem is that there's a force here and there's a force here, and so you don't actually get circulating electrons, which is what a current is. And so you'd have to conclude in this case the current is zero, and empirically this is what you find, by the way, if you're to do this experiment. Let's try another situation. All right, what if the coil moves in and out of the page, sort of like coming towards you? Would that in turn create a current? Well, the answer is that essentially your velocity then, let's say you're going into the page, well then your velocity is in the same direction as the magnetic field, which means that the magnetic force in your electron, the angle is zero, so sine of zero is zero, and so you should not get any kind of magnetic forces on the electrons, which means you should not get any kind of current. And so, and indeed, if you do this experiment, that's what you'll find. Alright, another option, here's another scenario. What if we spin the coil like this? Will this create a current? And the answer is actually no as well. And the reason that it's no is because if you apply the right hand rule and say, alright, well, we're going this, velocity is this way, magnetic field's into the board, so V cross B is this way, QV cross B is out this way. Likewise over here, our velocity is up this way, magnetic field's on the board, V cross B, QV cross B. So somehow the force is all like pointing radially away. And so again, that's not going to be the kind of thing that's going to produce a current. Alright, here we go. What if this happens, which is that coil is moving out of the magnetic field into a region where the magnetic field is zero? Does that produce a current? Think about it. The answer is yes. And the reason the answer is yes is because this part of the loop is still in the magnetic field, and so there's a magnetic force on the electrons in the downward direction, as I mentioned. But there's no like counterbalancing force on the electrons over here, And so, in fact, the electrons can circulate all around this loop. So that's really exciting, because you can induce a current in this thing. Which direction is the current? Well, if the electrons are going counterclockwise, the current would have to be clockwise, right? Yep. Okay. So this is really exciting, because thus far all of the power supplies for the circuits we've been thinking about have been batteries. They haven't been generators. So up to now in this course, everything we've been doing involves the idea that, all right, we're going to get these harsh acids and put them together, and that's what's going to create electricity for us. But the electricity in your house, that's not how it works. So the power plant isn't like sitting on this gigantic tub of chemicals, of electrochemicals of some kind. Instead, they're burning stuff, and then they're making things move, and then that movement is converted to electricity, and that electricity is what ultimately powers your house. So we haven't really talked quite about that just yet. Okay.
Consider a metal rod moving across.
Let me play this so you can hear the audio. This is a video from the book.
Consider a metal rod moving across a magnetic field. The Lorentz force, F sub L, acts on each charge within the rod. Some of the electrons are free to move, and they drift under the influence of the force. Being negatively charged, they flow in the opposite direction from that given by the right-hand rule for magnetic force. As the charges in the rod separate, they create electric fields until the electric force, QE, balances the magnetic force, QVB. Thus, an electric field equal to V times B exists at each point in the rod. This electric field creates a potential difference between the ends of the rod. The Lorentz force is therefore the source of the EMF. If we reverse the direction of motion, the potential reverses.
So, by the way, the book says the Lorentz force. I usually just call it the magnetic force, but it's two different names for the same thing. So, I don't know, just for fun, I decided to make my own demo of the electromotive force. So it is basically two particles that are attracted to each other. Whoops. That's right, the two particles that are attracted to each other. Maybe I can move this over here so it's a little bit more visible. Right, it's two particles that are attracted to each other, and so if you drag one, you can drag one wherever you want to, like that just goes where the mouse is. The fun thing is that the other particle is electrostatically attracted to this charge, right, this positive charge. And so there's some sort of Coulomb law going on to get it coming back. But the fun thing is that there's also the magnetic force. And so if you move it if I move it to the left, you notice that my little electron goes up as it goes. But if I move it to the right, my electron goes the other direction. And so it's a little bit like the EMF that they're talking about in the video. The only other thing I would say about the video is that you might wonder exactly how abstract this thing is, and my message to you is that if you had a multimeter on this piece of metal that's moving through a strong magnetic field, and you measured the voltage across, you would find a potential difference on it. It's not just some hypothetical effect, this is really what happened. So now we're going to talk about the electromotive force, which is related to all this, and the potential difference created by changing these kinds of changes is called the electromotive force. Moving through magnetic fields. That potential difference that arises is called the electromotive force. And then what we typically do is we figure out what the electromotive force is, then we divide by the resistance to get the current. So why do we do it this way? Why don't we just call it the electromotive current? Well, the nice part about saying electromotive force and thinking about it as a voltage is that you can have whatever voltage that you want on these items that are moving through the magnetic field. The current depends on what the resistance is, but the EMF itself only depends on, for things like the speed that you're moving through the magnetic field. So it really does make sense to divide it up this way and thinking about the potential and then think about the current secondarily. Just for fun, this is the EMF, not the International Monetary Fund, not the Impossible Mission Force. Anyway, so we've got so we have the ingredients now to make a generator. And so these are some generators. There's water pushing them around, and then they're converting that into electricity. As I said earlier, thus far in the course, everything has been batteries. And before they discovered a lot of this stuff, everything was batteries, in the kind of electric experiments that you could do. So this is the electromotive force. It's the derivative of what's called the magnetic flux. The magnetic flux it's a little bit like the electric flux from Gauss's law, except it's for magnetic fields. And there's a derivative there. There's a minus sign. I wouldn't get too worried about this minus sign. The main thing we'll be doing in this course is sort of absolute values. So I don't really need you to worry about whether the voltage is positive or negative, for example. And importantly, it's the derivative with time. So if the magnetic flux is changing, that with time, that produces an electromotive force. The magnetic flux looks like this. So again, this is somewhat similar to your Gauss's law with electric flux, but now it's magnetic flux. An important difference is that it's not over a closed surface. It's just over some surface, which may or may not be closed. And so this is what you would find from that. So if the magnetic field is constant, then remember, any constant in an interval, you can take it out front. Then you can rewrite this thing like this. The integral over the area is basically just the total area, and then the dot product gives you a cosine theta. So the magnetic flux in situations where you have a highly uniform magnetic field looks like this. And so if any of these three things change, the magnetic field, the area, the angle, that can produce a changing magnetic flux, and that changing magnetic flux can produce an electromotive force. If you stare at the units along this, you'll notice this is Tesla meter squared, which is also named after Weaver, which was one of the first great American scientists, actually. So, good job. All right. So this is what we get, again, for the magnetic flux. And changing any of these three things can produce an electromotive force. So changing the area, for example, changes the magnetic flux. We actually talked about this earlier. When that loop moved out of the magnetic field and into the region that had no magnetic field, that was essentially the area of the loop that's in the field decreasing. And so that is how you would explain the EMF in that case, the voltage that's in the loop. You can also change the angle between the loop and the magnetic field, which we'll talk about that a little bit later. Which, we kind of dealt with this a while ago, but we're going to talk about it again soon. And you can imagine how, as that thing rotates, there's moments where the magnetic flux is zero and moments where the magnetic flux is at its maximum. So we'll talk about that in a minute. But an interesting new thing here is that if the magnetic field changes, then that will change the magnetic flux. And this is actually a new idea. So we haven't yet talked about this. And it's actually quite different from these two cases for a couple reasons I'll talk about in a minute. So I think the next video is actually about changing the area. We're going to get back to this changing the magnetic field thing before too long.
When a wire cuts across magnetic field lines, a potential difference appears between its ends. The EMF that can be generated in this way is proportional to the rate at which the magnetic flux through the loop changes. To see why, recall that we can represent the magnetic flux through a loop by the number of magnetic field lines inside the loop. While keeping the magnetic field constant, we can increase the flux by moving one edge of the loop outward with speed v. Because the magnetic field strength is represented by the density of field lines, the rate at which the field lines enter the loop's interior is proportional to the rate at which the area of the loop is changed. Shrinking the loop reduces the magnetic flux and reverses the direction of the EMF. Increasing the rate at which the area changes increases the EMF proportionally, whether we increase the speed of the wire or expand the loop on more than one side at a time. However, moving the entire loop through the wire without changing its area results in no net change in the flux and results in no net EMF.
Okay, so again, we talked about this earlier, the loop that's moving out of the magnetic field. What we're going to do now is we're going to be a little bit more quantitative about it. And so we're going to say, all right, there's this length here, there's this width here. This width is actually, we're going to say this is x, and we're going to say x is changing. So x is, I believe x is this edge here, and it's going to advance like that. Okay. And so we can write down equations for what this looks like and assume that this is happening with a constant speed. So let me start the slide over again just to make sure. All right, there we go. So the area that is within the field is the length. The length's not changing, but the this part of it that's in the field is. And this width, because we're assuming constant speed, we can write down an equation for that. And so when t equals 0, x is back here, right? So at x naught. But as time advances, eventually x naught reaches this point, at which point the area is 0. And then it's out of the magnetic field and there's no more flux. So what we can do is we can actually take this equation, put it in, and instead of just sort of saying, is there a current or is there not a current, we can take this and figure out exactly what the current would be for this thing moving at a constant velocity. So let's go ahead and do that. This is one of the things that Faraday's law allows us to figure out. So again, this is the magnetic flux. The area is changing. The magnetic field is constant. And then the angle between the area, the area vector, the thing is perpendicular to the area. The magnetic field is not changing, right? There's no rotation here. So theta is 0 and the cosine just goes to a 1. So we can take the derivative of this now, because that's what you do to get the electromotive force. Right, so we're taking the derivative, and the magnetic flux is just BA, where B is a constant, so B comes out because B is a constant, and any constant you're taking the derivative of, you can move that out to the front. And then L is also a constant. I probably could have moved that out. But if you look at the things that depend on time over here, there's only one thing that depends on time, which is this Vt term. So you're going to end up with B times L, not necessarily times X initial, but definitely times V. I hope you can see that. You know, the minus and the minus. You end up with something like this. And then that tells you what the voltage in the loop is. So it's kind of, so imagine that the loop now has this a kind of a battery that has a voltage of this. We want to figure out what the current through that loop is. All we got to do is divide by the resistance of that loop, and that tells us what the current is. And again, the reason we talk about the electromotive force instead of sort of like the electromotive current is just because the electromotive current depends on the resistance of the loop, whereas the electromotive force does not. Like that, this voltage on the loop does not depend on what the resistance is. So that's good. All right. So I hope you noticed earlier that as we talked about the different situations with the loop and what does create current and what doesn't create current, I was often using the right-hand rule to say, all right, in this case, the electrons would get shoved this way, and maybe it would circulate or maybe it wouldn't circulate. It's always good to do that. What's interesting is that there are some cases in which that approach is either unclear in how you apply it or implies no current. Whereas Faraday's law does predict a current, and Faraday's law is actually right. So so it's always good to double check your result applying Faraday's law. And I'm going to talk about the funny cases in just a second. So it has to do with what happens when you take the derivative of the magnetic flux. So take the derivative of the magnetic flux. You can use what in calculus is called the product rule. And so if you have two things that are multiplied together, the derivative of the whole thing is the derivative of one plus the derivative of the other, kind of like that. Right? So the b here is changing, so this term is dB dt, and then the other thing is like a constant. And then this thing is b times the other thing, which is times the derivative of the other thing. So again, this is the product rule. Standard first semester calculus, nothing really fancy here. And all I'm going to do is say that we have names for these two terms, the helpful names, I think. This is called the motional EMF. And there's some examples earlier. So the examples we've been using so far, in which the magnetic fields have been constant, but like the wire loop is moving around, and we're expanding, and we're getting electromotive force. Those examples are the motional EMF. And what's interesting about the motional EMF is that you can use the right-hand rule force on electrons to confirm that there should be a voltage in those circuits. There should be a current in those circuits. There's various examples. I think you're going to list examples down here. Yeah, here we go. So that's an example of the motional EMF that we just did 2 slides ago. The other term here is called the transformer EMF. And again, this one has to do with if the magnetic field is not constant. Right? So if you have some permanent magnet where the magnetic field's not increasing or decreasing, this has nothing to do with that because the magnetic field is not going up. But if you have like a solenoid that's creating a magnetic field and you're increasing the current on that solenoid, well then the magnetic field inside of it would be going up, and you might have some interesting effects like this. So we're going to talk about that in the next few slides. Might be a video on the next slide.
In this demonstration,
so let me make sure you guys can hear the sound.
In this demonstration, both the area of the loop and the strength of the magnetic field remain constant. As the loop is rotated, the angle between the loop and the field lines changes. The magnetic flux, represented by the number of field lines passing through the loop, also changes. This changing flux induces an EMF in the loop, causing a current to flow. The magnitude of the EMF is proportional to the rate at which the flux is changing. It will vary as the loop rotates through different angles. When the rotating loop is perpendicular to the field lines, the flux is at its maximum. Because the flux is not changing much, the EMF is essentially zero at that point in time. When the rotating loop is parallel to the field lines, the flux is zero, but the rate of change of the flux, and therefore the EMF, is at its maximum. The induced EMF alternates between the positive and negative directions as the loop flips over with respect to the field. If the loop rotates faster, the amplitude of the EMF will be greater because the flux through the loop changes more rapidly. This method of rotating a loop in a magnetic field is used to generate the alternating current that supplies power to our homes.
So we're not yet talking about the increasing magnetic field. So that was rotating the loop in the magnetic field with a constant magnetic field. There's a nice example of how this works. That is one of the active figures from the book. For no especially good reason, they don't have this active figure in the text of the book. They just have it as this link on WebAssign. But in any case, there's this contraption that rotates around. You can see there's a permanent magnet here. So there's a uniform magnetic field, relatively uniform magnetic field in here that's not increasing or decreasing. And you can see that as it rotates, there's moments where you get a large voltage, and there's other moments where the magnetic flux is not changing as much. So in any case, the generators in most power plants are doing something relative to this. And you can do things like increase the RPM and show that the voltage goes up, things like that. It's a nice little demo. The reason that the voltage goes to zero has to do with, if you watch that video and just watch closely, there's parts of this cycle in which the magnetic flux is not changing significantly. It actually happens when the thing is close to flat with the magnetic field. At that point, the magnetic field is not changing all that much. It's mainly when the thing is perpendicular to the magnetic field and it's changing. That's when the largest change of the magnetic field is happening, and that's important because the EMF is relative to the change of the magnetic field, the derivative of the magnetic field. So anyways, that's a fun little thing you can play around with. All right, so an AC generator. So let's analyze this. So that is going to be motional EMF because really it's that loop is rotating, and I said that the magnetic field's not changing. So we don't need to worry about that just yet. So it's gonna simplify to something like this. I don't know why I'm so fuzzy right now. Someone will figure it out eventually. So we get this, and what we can do is we can actually make a simple model for what the angle might be doing. So let's say that the angle is rotating in a constant angular velocity. So we can write down some equation for what that looks like this, and then we can take the derivative of this and find that d theta dt is just omega, which means that the electromotive force looks like this. And so you can see that there's parts. There are moments when the angle is equal to 0, and sine of 0 is 0, therefore the EMF is 0. So and you can see other things like if you make the RPMs larger, well then it's going to increase omega, and that's going to increase the electromotive force, things like that. So quantitatively, this is how This is how that works. All right. Now we're finally gonna talk about the magnetic field increasing or decreasing. So let me make sure the sound is good.
In this example, we keep the area of the loop constant and alter the strength of the magnetic field. The EMF induced inside a conducting loop is proportional to the rate at which the magnetic field changes in the region containing the loop. We represent the strength of the magnetic field by the density of field lines. As the field is increased in strength, an EMF is induced in the loop, causing a current to flow. If we increase the magnetic field at twice the original rate, the induced EMF and the current in the loop will be twice the original amount. Decreasing the field moves field lines out of the loop and produces an EMF acting in the opposite direction.
So that was a nice visualization of the transformer EMF. My comment on that video is that you cannot explain that current with the right-hand rule, because the right-hand rule ultimately, you're trying to figure out what the magnetic force on the electrons is. Magnetic force is F equals QVB. And so the electrons in that loop have zero velocity, right? And so the magnetic field can get as large as you want. It's not going to produce a magnetic force on the electrons, because 0 times something big is 0, right? And so you cannot use that to explain this. So what causes the transformer EMF? Hope you appreciate the transformer logos here. What causes the transformer EMF is a bit of a long story. The best way that I try to explain it is, at this point, is essentially saying, all right, well, the electrons have zero velocity, so the magnetic force in the electrons is zero. But is there some other way of explaining? Like, let's try to think of other possible explanations for this thing that might work. And so one of them might be saying, all right, well, the magnetic field's not exactly parallel. It's like at an angle, and so there's a component of the magnetic field that's at this thing. And then so that it's, so maybe that has something to do with it, but that, it turns out, you can't explain it with that. You might wonder, okay, well, there's electrons, but they're wiggling around, and so they have some random velocity in each direction. Like, we had a whole thing about that, about how the electrons are bouncing around the conductor. You might wonder if that random velocity, starts to get it going, and then somehow there's this sort of runaway effect that ultimately produces a current for the transformer EMF case. That actually doesn't work either. The real answer has something to do, basically has something to do with relativity, which I hope we can talk a little bit about in this course. But it's one of the hardest things to try to explain in this course. So this is a drawing from the book that I put up here, because it's interesting to me that it shows that as you bring the bar magnet closer to this thing, you are increasing the magnetic flux, and then you induce a current on this thing that so that this wire loop produces a magnetic field in the opposite direction to it. But interestingly, if you pull the bar magnet away from this thing, it will induce a current in the opposite direction that actually will well, that'll produce a current in this direction, which will make a magnetic field this way. So it'll try to strengthen the magnetic field that's inside of this thing as the magnetic field is decreasing, which is interesting. So yeah, so that's an interesting sort of related phenomenon, and and again, this is another example of transform EMF. That's why I'm showing it here.
Thrusting a magnet suddenly into a coil of wire induces an electromotive
This is a video
force
from the
or
book,
EMF
and so this is
in
a
the coil,
demonstration that I
as
sometimes do in the
demonstrated by the
classroom when we're
motion
not
of the
in the pandemic.
galvanometer needle.
And
Notice
you're
that the
taking a bar
EMF
magnet
quickly
and
falls
putting
to
it
zero
in this coil
once
thing.
the magnet is
There's
no
no battery
longer
here,
moving.
which is
When
interesting.
withdrawn,
Right?
an EMF
There's just this
appears
big
again,
coil. This is
only
basically a
this time
solenoid.
the needle jerks
There's
in the
just this big
opposite
coil,
direction. The
and
magnetic
the coil's
field
at
of the
rest,
bar magnet by
and
itself
so the
does
magnetic
not
flux
produce the
increases.
electromotive force.
And if the magnetic flux increases, that's going to produce an EMF,
only
and
when
that
the
EMF is
magnetic
going to show
field
up here
lines are moving across the
because we're
wire.
measuring the voltage across the thing. So this is a real thing, and as you can imagine, this is kind of a power source. One interesting thing is that when you are if you're pushing this bar magnet into this loop and this current is generated, the magnetic field is opposite to this north pole, and so it actually kind of resists it. It actually kind of slows it down some. Whereas here, if you pull the bar magnet away, this thing creates a magnetic field this direction that actually kind of attracts it, because just like a bar magnet would, if that makes sense. So if you have a north and a south bar magnet, they're going to attract each other, and so that's kind of what you get here. Whereas here, it's like you have a north and a north bar magnet, and they're repelling each other. I mention all this because this is the principle behind electromagnetic braking. So the exact details are hard to explain, but basically, the fact that when you're pulling this thing away, and it's slowing this thing down while creating current, well, if you can capture that current, put it back on the battery, then you can use that energy later to, drive the car further, things like that. So this is the basic principle behind regenerative braking. I wish I had more time in this course to go into that, but fortunately I don't. So that's kind of what these slides are basically saying. Yeah, and we'll talk later about railguns. This is the principle behind railguns. All right.
When a magnet is moved near a loop
So
of
let me make
wire,
sure you can listen to this video.
When a magnet is moved near a loop of wire, the induced field acts to oppose the motion of the magnet. In general, the induced current always appears in such a direction that it opposes whatever change produced it. This fact is known as Lenz's law.
Okay, so the last thing, and this is actually related to the worksheet. So this is the jumping ring experiment. And there's a big solenoid here, and there's a piece of iron, and there's a current source, voltage source. The DC power, again, that's just constant current, and they're going to put a little piece of aluminum here, so a ring of aluminum, and so when you connect this thing, the magnetic field increases dramatically, which produces an EMF in the ring, but the important thing is that the EMF in the ring produces a current, which produces a magnetic field. That magnetic field is opposite to the magnetic field, and it resists, and it actually causes it to fly upwards. Hello? I sent the call as a texting. I'm ready for them to either